Okay, so first of all, just to start up, this presentation is just too good. I'm just kidding. Just want to lighten up everyone's atmosphere. So what is this presentation all about? Well, this presentation looks at something called as consensus and commit infrastructure. Basically, the authors are trying to present a framework which includes both consensus and commit protocols. And the aim is because both consensus and commit protocols try to achieve fault tolerance. So they're trying to see if we can encompass all the states into a single model, which they call as a unified model. And how do they come up with this unified model? Because they have tried to see that both consensus and commit protocols share similar states, which we'll see later on the presentation, what are those similar states. And based on that, the aim is to design one common model. So in this specific paper, they are looking at both types of databases. They're looking at partition databases and replicated databases. Partition databases are basically a form of sharded databases, and they have been traditionally used to ensure that each partition holds a unique set of data. And to ensure that in the partition databases, there can be transactions which require access to multiple partitions. They call such transactions distributed transactions. And once there's a distributed transaction, there's a need to ensure that there's an ordering, because a distributed transaction requires access to multiple partitions. Some partition will access data in some order, some will partition another way. So that's why there's a concurrency control protocol. There are already a lot of concurrency protocols exist, like 2PL, MVCC, timestamp, and several of them. But when there's a concurrency protocol which actually is running, each partition still ends up creating its own order. For example, partition A might want to commit transaction because according to it, a transaction T, so there are some distributed transaction and there are some local transaction, and local transactions happen in each partition, while distributed transactions have to be synchronized basically. And that's why one partition may want to commit while other partition wants to abort. And such scenario, what we require is sort of a coordination among the partitions, and basically determine what is the global fate of this transaction, whether we want to actually commit the transaction or do we want to abort the transaction. And traditionally, there have been protocols which suggest that protocols are called as commit protocols to ensure agreement among the partitions. And 2PC was one of the first protocols which was proposed by Gray and other authors subsequently. So what does 2PC protocol say? It says that, hey, there are a lot of these partitions, and let's make one of these partition as coordinator, and let all other partitions behave as cohorts. So coordinator will start this process of agreement, and all cohorts will join the process. So there have been a lot of commit protocols. Why? Because even the 2PC, we'll see it's very easy to go, but 2PC is blocking. There are very simple ways to show that if you make a coordinator in a cohort fail, then all the other cohorts might just stay wherever they are. They cannot make any progress. The system just gets blocked. So there have been a lot of non-blocking protocols like 3PC and several other protocols. So let's try to see what 2PC basically does. So the diagram which we are using for this presentation is one which has been specified by the authors in their paper. One of the key reasons is because they follow this whole structure for their own unified framework. So in this diagram, if you'll see, there's on the left-hand side, there's coordinators behavior. On the right-hand side, there is cohorts behavior. So when coordinator, how does this start? So in a partition database, when client sends a transaction, and if it's a remote transaction or it's a distributed transaction, the coordinator which gets the transaction, he sends that transaction to everyone else. Now everyone will run their own concurrency control or global concurrency control, whatever it is there. And then once the transaction has completed at each participant, now it's a time of running this protocol. So this is what this message is. This message is basically saying that now it's time to ensure what is the common decision, whether they want to do commit and or abort. So coordinator basically sends votes to all the cohorts. When any cohort, he basically tells them, hey, tell me, what do you want to do with this transaction? Do you want to commit or abort? Commit means people will reply with yes. Abort means people will reply with no. And then they send their votes to the um, coordinator. Now, based on everyone's vote, coordinator decides a global decision. If just one person says abort, the transaction has to be aborted. If everyone says commit, then it has to be committed, and he sends that global decision to everyone. Everyone uses this global decision, and then they reach a common state. So basically, authors say there are two states, two phases basically. There's a value discovery phase and there's a decision phase. That is what is happening in the two-phase commit protocol. And these are two phases that they've derived, and later on we'll see how they put these two phases in their own general framework. So till now we talked about partition databases. Now we are going to talk about replicate databases. And replicate databases we all know because we have been looking at all the past presentations. So assumption here is that each server is acting as a replica. Everyone has the same set of data items. And what authors are using in their paper as the main algorithm for replicate databases to ensure same ordering is Paxos. And Paxos, what they're trying to propose here is a primary backup model, Paxos model. And yeah, so here there will be some proposers and acceptors. Proposers same as leaders, acceptors are same as cohorts. And let's see what the diagram is according to them straight away. So if you'll see here, in case of replicate databases, when the proposer gets a request from the client, now he's trying to first start the leader action. So there are, in this paper, they've used two different models. There are some places where the use idea of leader action is actually happening. And there are other places where they assume the leader has already been determined. In two pieces, the leader is already determined because the person who gets the transaction is the leader, that partition is the leader. In Paxos, they're saying that leader discovery is happening. And so every proposer, whoever gets the request, he will now send a Pax prepare message basically to ask every acceptor that, hey, do you want to choose me as the leader? And then if he gets a majority of Pax prepared message, basically every acceptor who gets the Pax pre-prepare message or prepare message, he sends a Pax prepared message to everyone else. And once he gets a majority of Pax prepared messages, he now sends a Pax propose message. Basically, he proposes this value or this request. And once he gets, once a acceptor gets a Pax propose message, he sends a Pax accept message. And once proposer gets a majority of Pax accept message, he sends a apply message. And that's when every acceptor assumes the decision is final and it concludes. Obviously, there are many cases which can happen here. It is possible that a proposer may not actually get majority. In that case, he will time out and he'll start this phase again. It is again possible that he might have cleared this stage, but then there was another proposer who succeeded, and then again he'll also time out. So those multiple timeouts can actually happen in any manner. But this is the basic flow that what they're trying to show. And yeah, so that is the main of, and moreover, what they want to show is that there are also three phases here. There's a lead election phase, there's a fault tolerance phase, and the decision phase. This decision phase we also saw in the 2PC protocol. The two new phases, what they're talking here are the lead election phase and the fault tolerance phase. So basically in their whole structure, what they learned from the 2PC protocol and the Paxos protocol is that they both have some common phases and some different phases. So in 2PC, we saw two phases, and Paxos, we saw three phases. This helps them to abstract a model where they say that a unified model for consistent commit would consist of 4 phases. It will consist of a leader election. Paxos will require a leader election, while 2PC assumes a pre-designated leader. But if a failure happens in 2PC, then a leader election has to be done. Followed by that, there's a value discovery. So in 2PC, what do they mean by value discovery? Basically, the coordinator asking all the cohorts, tell me your vote. So that is what this value discovery is. In case of Paxos, if a proposer basically is unsuccessful, then in that case, the acceptors would have given him a prior value. So he uses that value. That is what they call as leader discovery in both, value discovery in both the protocols. Fault tolerance in Paxos, as we could see, is that because there's a majority of words asking, and he's ensuring that everyone is actually accepted and everyone is applied. So that is a part of fault tolerance in Paxos. In 2PC, the fault tolerance happens through logging, but obviously Paxos is more fault tolerant than 2PC because 2PC requires access messages from all the cohorts. If it does not even get one, then it just gets stuck or it has to be moved forward. Decision, at the end of a decision happens in both the protocols. Whenever the cohort, whenever the coordinator or the leader is able to make a decision, he sends the decision to all the acceptors or proposers. That is the whole point. So this is their unified framework. If you, in their unified framework, the first phase redirection followed by value discovery, fault tolerance, agreement, and decision. And what they want to say is that depending on the type of the protocol, whether it's 2PC, Paxos, or any other protocol, it will use some of these stages. Not all stages are required, but some of these stages are required. So let me just go over this whole diagram quickly. So the first stage is depending on the protocol. So in case of Paxos, when the leader will get a request, he will now start the leader election. Basically, it'll send everyone to ask everyone, hey, do you want to elect me? And then everyone will send their votes whether they want to actually elect him or not. And followed by that, value discovery. Value discovery may not happen in Paxos, but it may happen in 2PC, because at this point in time, coordinator would require everyone's vote. So that is what everyone's vote he's getting. Now, fault tolerance is a part of, is implicit in 2PC because everyone is logging, but in Paxos it has actually happens through agreement, where leader is trying to ensure that everyone is actually agreeing. And then decision phase applies to both the protocol, because everyone is trying to see whether, coordinator is trying to see whether everyone has agreed. And now when there's a common vote, he just sends to everyone, so then I can apply. This is the basic framework for CNC, which they call as CNC. Basically means as consent and commit framework, a unified framework. What this is the main focus of the paper according to the authors. So now that they have this CNC framework, they want to apply this CNC framework to different applications. Basically, they want to show that this framework can be used to solve existing systems. And so what they'll do is that first they'll show there's a sharding only system, then they'll show there's a replication only system, and then they'll try to show a system which includes both sharding and replication. A sharding only system is the same style of system which you have already seen, where 2PC style protocol will apply. And as we already mentioned, that 2PC is blocking, so not all the systems use 2PC. A lot of systems use either 3PC, but even 3PC has, the problem with 3PC is that it is not susceptible to message loss and message delays. That's why there's another protocol called E3PC, and they represent their own algorithm, which they call as Paxos Atomic Commitment Protocol, or PAC. And PAC is similar to E3PC. And so now we'll see what basically they mean by sharding only system, or how does their PAC protocol works in this system. So for this protocol to work, their PAC system, they need some set of variables. So they basically look at 4 variables. There is something called as init val, accept num, and decision. So what is init val? Now, as we saw in 2PC, there was basically when coordinator asked every cohort, tell me a vote. So this vote basically is sent in this init val variable. And then once coordinator makes a decision, he sends it through accept val. Accept num is basically identifying, basically it's sort of a sequence number or sort of an identifier. And decision is basically the final decision. Mostly, if you'll see, I'll show you later on that these variables are basically used during fault tolerance. That is what their aim is. So this, if you'll see, this whole diagram still comes from this CNC model. In their CNC model, initially they had leader election and value discovery 2 phases, and they merged those 2 phases into single phase because they said that not every time for a sharding system they require leader election. So that's what the whole point is. But value discovery is also it's not also always required. So that's why they said that it's a Paxos protocol. So that starts with similar manner. They ask for request. When coordinator gets a request, he asks everyone, do you want to elect me? Everyone says, okay, whether we want to elect or not, they basically give their vote. This is the initial vote, they send the initial vote. Now, once he gets everyone's initial vote, he now knows what's the value that everyone is ready to agree on. And then he sends that value to everyone else. And once everyone gets that basically he sends the decision, sorry, value, and once he gets agreed value from everyone, he now ensures that okay, everyone has that value and he has applied to everyone. In some manner, this protocol is quite similar to 3PC because 3PC also has 3 phases, where basically the first phase is basically where the leader basically start by sending, give me a vote, everyone sends a vote, and then he sends them pre-commit, and everyone does this pre-commit, sends a reply, and then he does actually abort a commit. So basically there's an extra stage which is similar to what 3PC is doing. The names are similar to their framework, but I myself see this protocol quite similar to what 3PC is doing. Now, how does their variables actually help in this thing? So the variables, if we look at this thing, then init val was being used here. Except was used here because once he made a decision, he sent except here. And the decision variable, once he got everyone's agreed vote, he sent decision through this thing. Now it is possible leader died and the system only considers some cohorts. Some cohorts got information, full information. Basically, some of the cohorts reached the pack apply state. Some cohorts didn't. Some cohort was stuck at this stage. Some cohort was stuck only at this stage. Now we need to make a recovery. So at the recovery, all these sharding only protocol, whether it's 3PC or 2PC, they all suggest that, hey, you have to select a new leader. Now, once the new leader comes, he has to basically get everyone's state. And once you get everyone's state, now you need to decide what is the state to follow. So now the whole point is, if suppose there was any person who reached this state, basically he got this decision variable as true. So the decision variable would be either true or false. So if somebody reached this place, then for him decision variable was true. That means that the new leader can actually determine that that transaction got completed, the decision was actually made, and now he can basically send that variable to everyone. So now he knows whatever the decision variable is true, he knows what the decision, whether it was commit or abort, and he can send that value to everyone. We can distribute it to everyone. But suppose nobody actually reached to this stage, everyone was either here or here, then still there was someone for whom this except val was true. Basically, everyone sent their vote init val, and now a leader was able to find a decision and sent everyone some decision here. So based on that also, he can at least come to know what was the decision which was made prior to failing of this leader, previous leader. And using that, he can now continue the rest of the protocol. So this is the whole idea of Pact. That is how Pact provides fault tolerance in sharding only systems. Now let's see the other model. Their other model was replication only in the cloud. Basically, they're saying that now they're going to consider a very simple system where the whole idea is it's all replicated, and they call a protocol called as RPack, which is similar to a previous works by a subset of the author, which they call as replicated commit. In my opinion, RPack is quite similar to what Paxos is, and the whole idea here is that because in this protocol, if you see in Pact, at this point, leader needs messages from everyone. He needs messages from all, but in RPack, he only needs messages from majority of people. And that is what is quite similar to intuition of Paxos. So that is what RPack is doing. There's not much in the paper apart from this section. So finally, they move to another part, which they call it sharding and replication. Basically, now they're assuming an infrastructure where there will be sharding also and replication also. And for that, they'll consider two design strategies. One is state machine based, another is Pact. So the first one is basically a layered architecture. And what they assume in this layered architecture is basically there will be a lot of shards, and within each shard, there will be a set of replicas. So basically, as we can see, this is basically a sort of a hierarchy. And between all of these shards, there will be 2PC protocol, which will run. So now let's assume we have 5 shards. And in these 5 shards, the client transaction can come to any of the shard. And whichever shard it comes to, that shard's replica will act as the coordinator, and now he'll ensure the 2PC among all the other shards. And whenever a decision is made for any state of the 2PC, that trickles down in all the replicas of that shard. Basically, Paxos run within the shard, and 2PCs run among the shards. So that's why they call it 2PC/SMR architecture. That is what they're calling it. Another style of architecture which they call is called as basically they call it a state where they say we just flatten it out. So is the assumption still that there will be n shards or 5 shards, and each shard will have some set of replicas? That assumption is still there. But the difference here is that instead of running 2PC among the shards and paxos within each shard, they say that no, we'll trickle down every message completely. So in some way, I see it as a manner that whenever there's a message, that message is now going directly to all the replicas and every replica is communicating. So in this case, if you say, assume there are n shards and each shard has n r replicas, so total number of participants n into r for one transaction. So now we can run the Pact protocol directly among all of these servers. Basically, say suppose, let me go back to the old diagram. So Pact, yeah. So when when coordinator gets a message, and coordinator could be the one who gets the request from the client. When he gets a message, now in that case, he will send this elect me to everyone, all the n cross r replica. Instead of just sending to one replica in each shard, he's going to send to everyone, and he'll wait for a reply from a majority of replicas from each shard. So if there are n shards and each shard has r replicas, he'll wait for r by 2 plus 1 replicas from each of the n shards. That was his time is. And once he get that many messages, now he moves to other phases. So basically they have these two new variables, which they call superset and supermajority. Superset is basically used for how many replicas from each shard he needs to wait for the first stage, basically to get the votes. And supermajority is just for next stages that apply in agreed phases. That is used for them. So now let's try to come to the evaluation of this paper. For evaluating, the authors have used EC2, and they've used machines. Each machine had 2 cores, and they used five data centers: North California, Virginia, Ireland, Sao Paulo, and Tokyo. For concurrency control, they used 2PL. And for benchmarking, they used YCSB. They also have TPCC, but I'm not going to concentrate on TPCC experiments in this presentation. They have used a system which has 10,000 data items, and their whole experiment includes only 2,500 transactions per run. They have run, to ensure average of results, they have run it 3 times. So they calculate what is the round trip time, because now they're going to run experiments across these global data centers. And obviously in like North California and Virginia, the latency is, round trip time is the least, while between Tokyo and maybe Sao Paulo, it's the maximum. So that is what all the numbers are. And one of the most interesting experiment I found was the one where they showed that what happens if we vary the number of shards. I mean, so instead of having just one, we can have 1 shard, 2 shard, 3, 4, 5. What this basically means is that there's a distributed transaction which requires access to multiple shards, and it might require access to 5 shards. So their claim is their GPAC will outperform the traditional way of 2PC SMR. 2PC and SMR is being used right now by Spanner, and authors claim GPAC is a protocol which they have designed, but they also said it shares similarity with other protocols like Tapir and all. I have not read Tapir, so I cannot say anything much about it. But yeah, that is what is happening here. And according to them, as the number of shards are increasing, GPAC gains much more over other protocols. So these are some of the takeaways from me while reading the paper. I'm not saying these are the takeaways which authors have noted on, just my views. So one of the things which I see is that GPAC raises an interesting struggle between inter-cluster and intra-cluster latencies. I mean, these numbers, although were interesting, and here it is being shown that GPAC actually wins over 2PC SMR. But I believe there's a important play here that in their evaluation, they use a set of transactions which is 2,500 transactions per second, and that there are only 10,000 data items. If this number changes, then it might actually differ. Moreover, their claim is GPAC requires only 3 round trip time latencies because it's basically running Paxos, while 2PC SMR, it requires 2 round trip time in 2PC and 3 round trip time in Paxos within. But the 2 round trip time, with what I see in the Paxos is in 2PCs only in intercluster. So there are only few misses intercluster, while more misses are happening intra-cluster. Intra-cluster is not costly because if it's within just one cluster, within one cluster, the round trip time could be very less compared to within clusters. And we have seen in some other works which have shown that intra-cluster latency is just often less than 1, and bandwidth could be more than, and bandwidth intra-cluster could be at least 10 to 100 times more what is between the clusters. Moreover, I'm not sure what architecture is being used in the paper, but things like request batching, multi-threading, pipelining may tilt the graph in favor of 2PC and SMR. So that's just my personal takeaway. Thank you very much.